When you're dealing with these functions defined on the unit circle, you need to consider domain values. What works and what doesn't. Remember, we define that on the x-axis and on the y-axis. There are some functions that are undefined whenever you're dividing by 0. So recall the functions that we have. Let's say we've got the function. What is their domain? And what are some notes? Okay, we have 6 functions. The first function is the sine of t. The second function is the cosine of t. The third function is the tangent of t. And then we have their reciprocals. Okay, remember that sine on a unit circle is y. Cosine is x. Tangent is y over x. Cosecant is 1 over y. Secant is 1 over x. And cotangent is x over y. Now, for a domain, for x and y, I could plug in any x or y that I want to. That means that sine of t and cosine of t work for all real numbers, which is abbreviated with this fancy little symbol, 2 lines and an R. You'll see it in some textbooks where it's a bold line followed by an R. That stands for all real numbers, which means that you can go from negative infinity to infinity. And it's not all numbers, it's all real numbers, because there are complex numbers in math which are non-real numbers, they're imaginary. The domain of cosine is also x. So there are no notes here. Everything works, we're good to go. Tangent's a problem when x is in the denominator. And so we need to know when x is in the denominator is 0. When is x 0? On the unit circle, on the y-axis, those are the points 0, 1 and 0, negative 1. What does that correspond to in terms of degrees and pi? That is pi over 2, or 90 degrees, and that is 3 pi over 2, or 270 degrees. So notice that's off by 180 degrees. So every time I add pi to pi over 2, I'm going to get some 0. Every rotation here that I go through is going to cause a problem. Because every time I add pi is going to be an issue, I need to consider pi over 2 plus any number of pi's, where n is any integer. So n could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 0, negative 1, 2, 3, for all integers. And so this case, n is in the set of integers. This representation, that's a z, kind of like the r, where n is an element of integers. So n is an integer. So how could I write this with a common denominator? I'm going to take it over here, and I have pi over 2 plus n pi, 2n pi over 2 to make a common denominator. And that's the same thing as 2n pi plus pi over 2. Factoring out a pi, I can write that as 2n plus 1 over 2. So you will see the domain as t cannot be equal to 2n plus 1 pi over 2. You have to exclude odd multiples of pi over 2. The way that I'm going to write this is I'm going to say for all t such that t cannot equal 2n plus 1 pi over 2 for all n in z. What the heck does that mean? This is saying for all, that's what the upside down is, n, that's an element n, and then again z, remember, is integers. It's a special character that we use to represent, so it's shorthand. And this means cannot be. Now I'm saying to exclude odd multiples of pi over 2 because it's not every pi over 2 that x is a problem. It's every pi. And so 2 pi over 2 is just pi. That's not an issue. It's only pi over 2 and 3 pi over 2 that's an issue. The same thing is going to be true when I have secant because x is in the denominator there. So we're going to say that for t such that, this means such that, this is set notation here, t such that t cannot be equal to 2n plus 1 pi over 2 for all n in z, meaning for all integers. Make it a little bit prettier. Same notation, exclude odd multiples of pi over 2. All right, what about cosecant? When is y equal to 0? That happens on the x-axis. On the unit circle, that's at the points 1, 0 and negative 1, 0. And that happens, again, every multiple of pi. So that's going to be at 0 and pi, 2 pi, and so just multiples of pi. And the way that I can write that is just n pi. So I'm going to write that as t such that t cannot be n pi for all, and actually I don't even need to write the 4, I could just write the a, for all n in z, which again means for all integers. So I exclude multiples of pi. The same is true for cotangent because y is in the denominator there as well. T such that t cannot equal n pi for all n in z. We exclude multiples of pi. Here is the domain information. Sine and cosine don't have any restrictions. Tangent and secant are odd multiples because that is when you have pi over 2 or 3 pi over 2 when x is 0. And then cotangent and cosecant when y is 0, you have n pi. So your multiples. And notice that that happens on the axes only.